Q weighting in phonetics is full of interesting topics, and in this talk I'm going to share with you some ways that we've learned about the auditory system by studying Q weighting, or how we can think differently about Q weighting by considering auditory processing. So we're going to want to think about auditory concepts like excitation patterns and cochlear mechanics and neural synchrony and so on. The main idea that I want to convey today is that you can learn a lot about hearing or hearing loss by studying Q weighting. The overview of what I'll talk about starts with some understanding of auditory encoding and degradation, cochlear implants, and some basic findings that won't shock you, but will set the stage and confirm that we're on the right track when we think about things like spectral and temporal cues. Then I'll show you some more surprising findings and cool ways that visual cues are weighted in a way that's compatible with phonetic gestures, how we incorporate the lexicon, and how we accommodate acoustic differences between talkers. Just as the same phonetic feature can be conveyed with multiple cues, I'll share some ways that the same acoustic cue can be encoded using different biological mechanisms. And finally, I'll share a neat new direction where we identify a tipping point between Q weighting and Q integration. This work has been done with numerous co-authors pictured here and with grant support from the NIH and IDCD. A lot of the people on the screen are what I'd call auditory scientists rather than phoneticians, and so they might use a slightly different vocabulary than phoneticians when talking about some concepts that we all are referring to. For example, when looking at a speech signal, we describe things like the envelope, the slow overall changes, periodicity, which are the repeating elements that you see here that differentiate between voiced and voiceless speech, and then if you zoom into the microscopic level, looking into what we call the temporal fine structure, which are all the fine details of the signal, like the different frequencies that you'd see in a spectrum. But we think about a spectrum like what we see here for the vowel E. The spectrum that you see on the computer is not really the spectrum that your auditory system would recover, say at the level of the basilar membrane or the inner hair cells. You'd really see a much more smooth representation like this because of integration across different neural populations. And this is just for one stimulus presentation level. As it turns out, when you change the intensity, the spectrum itself doesn't change, but the auditory representation does change considerably. If you lower the presentation, you actually have a much cleaner, more precise representation of the signal, but if you raise the presentation level, it becomes even smoother and more degraded. So when you think about the auditory system, we're really thinking about logarithmic rather than linear scaling of frequencies, so this is just a way of viewing that. Let's take, for example, this high-level excitation pattern. It's pretty smeared, it's lacking in detail, and this is actually representative of the excitation pattern for someone with hearing loss, because damage to their auditory system means that they're actually losing that frequency tuning and active compression that would have otherwise retained all the details in the speech. And for people who use cochlear implants, the problem is even worse, for reasons that we'll discuss soon. Unsurprisingly, the loss of spectral detail has some consequences for phonetic perception and Q weighting. For example, if you consider the vowels in the words seat and sit, you'd normally identify them according to the frequency patterns that you can see here in red, but if you take away the spectral detail, you'll notice that those frequencies aren't resolvable anymore, and so it becomes more natural to rely on things like the duration of the vowel. And indeed, our group and other groups have shown that people with cochlear implants rely less on spectral cues and more on temporal cues compared to people with normal, typical hearing. Even in the spectrum itself, there are cues that are really constrained within a tight frequency region or expressed over a wider, more coarse frequency region, and those more coarse cues are preferred for people with cochlear implants as well. It should make sense that if you're differentiating this formant peak from the one right next to it, or the whole span that differentiates, say, a B from a D sound, you need some basic psychoacoustic ability, or auditory acuity. The way we can test this normally in the auditory domain is using a controlled stimulus like this, that has equally spaced peaks and valleys in the spectrum, in this case, one every other octave. So what we would do is give you a spectrum outlined in red here, and see if you can differentiate it from the spectrum outlined in purple. And this would be actually a pretty easy one to differentiate, but what we do is make those peaks and valleys denser and denser until you can no longer tell those two sounds apart. And that should be linked to your ability to hear those differences in the formants. We can also look in the time domain, for example, for a voice onset time contrast. If we zoom into the onset of that syllable, we can see that the timing difference between these sounds could be expressed as a temporal modulation. So the way that we test this in the auditory domain is by giving you some modulated noises or other sounds where we can change the depth of modulation and see how much depth you need before you can't differentiate it between a steady envelope sound. Conversely, we can give you sounds where the rate of modulation is what's changing, and we can see how fast you can detect those changes in modulation. In the case that you have a word that could go one way or the other, like this case between bap and gap, you'll more likely choose the word gap because it's a word and bap isn't a word. This phonetic contrast turns out to be very difficult for people with hearing loss, just like any other place of articulation contrast. And so when we give them this, they show this same lexical bias effect or Ganong effect, where if you change the phonetic environment, they would of course prefer the other choice because back is a word and gak isn't a word. So what Stephen Giannakis and I found in our 2019 JASA paper was that in people with cochlear implants, this effect is expressed even more strongly, and stronger still for faster phonetic contrasts, like stop sounds, compared to slower phonetic contrasts, like fricatives or vowels. So one thing you might be wondering is, we're talking about the auditory system, but we also use our visual system to weight phonetic cues, and so we can think about visual cues to what syllable is being said. For example, we can see things like lip rounding, where for a word like si, you'd see the lips retracted, and for she, you'd see a little bit more rounding in the lips, just as you would for shoe. But to fill out this quadrant with the word su, as it turns out, it groups over with the rounded sounds because of anticipatory coarticulation with the u. The point to draw from this is that when u is the next vowel, lip rounding doesn't tell you a whole lot about what the consonant is, whereas if the vowel is e, the lip rounding really does help you differentiate the consonant. So to simplify this, for e, lip rounding is informative, but for u, lip rounding is not so informative. So to test this out, we ran an experiment where you heard sounds ranging between sh and s, and you just identified them and we kept track of your categorization, producing a function like this. And you saw a face where the lips were either rounded or not rounded during the consonant, and so if there were an effect, we'd see that function shift to the left or the right. We had 4 different groups: people with normal hearing, people with cochlear implants, listening to syllables that end in an e or u, and we would expect that the effect of lip rounding would not be very strong for u, and in fact there was no effect. But in the context of e, there was a little bit of an effect. So if you saw the lips unrounded, you were more likely to think that the sound started with s. So e is more informative than u, but for people with cochlear implants, as it turns out, there was a little bit of an effect, even with the u, so maybe they were picking up on some more subtle details of the articulation that the people with normal hearing weren't really tuned to. But the really cool effect was, in the context of e, people with cochlear implants showed an enormous effect of lip rounding. So what we're learning is that the influence of lip rounding is not really restricted to the individual phoneme, but it depends on the vowel context, it depends on the sequence of phonemes, and is also moderated by your hearing status. What we're learning from this is that listeners or observers appear to have some tacit understanding of the compatibility of lip rounding across sequences, like they're sensitive to coarticulation. So going back to this idea of this little cartoon spectrum, just showing that sh is lower frequency than s, but this, of course, is affected by the gender of the talker. So for Ashley's voice, we draw the boundary between these two phonemes maybe here, but for Pavel's voice, all the frequencies are shifted a little bit lower, and so we'd have to adjust our boundary accordingly. The way we test this experimentally is by creating a fricative continuum spanning from a low sh to high s, and then appending a voice to it. For example, we can take a vowel spoken by Ashley or by Pavel and just attach it to the vowel. We can take his voice, put it on there, and all we're doing is changing the context of the fricative and seeing how that context works backwards to affect your perception of what came right before it. So if we look at the data here, this would be our labeling function for fricatives when the following vowel is spoken by a woman, and here's where that vowel is spoken by a man. So again, we're talking about the effect of the vowel part, not the effect of the fricative itself, because that's actually what our continuum is, but it's the vowel that contains the cues for the gender that work backwards to affect your perception of the fricative. So for a woman's voice, our crossover point would be right over there at step 6, but for a man's voice, it would be over there at step 4. So there are other effects, not just the gender of the talker, but for vowel rounding, formant transitions, and other things that have been found for the last, say 40 years or so. but the way to think about it is that a lower frequency sound is acceptable as a high frequency when spoken by a man. So again, we can think about not only the acoustics, but the visual cues for this, because you can think about what a person's voice should sound like even before hearing them. For example, you know that her voice should sound a lot different than his voice. So we tested this using auditory visual stimuli, where we paired the visual cues for gender, or either match them or mismatch them with the auditory cues for gender. And what we found is for listeners with cochlear implants, seeing the face pushed the auditory perception in the same direction as when the vowel was actually spoken by that person. So if we mismatch the gender, the visual gender cue acted sort of as a proxy cue to give some clues for which way the auditory perception should go. So we've already learned a little bit about this, but we have a lot more questions about how this effect works. So for example, how quickly does this context effect emerge? Do we see phonetic accommodation in the auditory domain for people who use cochlear implants? What acoustic cues are used for this phonetic accommodation? And are the cues the same for people with normal hearing and with cochlear implants? And is this effect related to the way that we perceive pitch? So just to remind you, the effect we're looking at is when we measure the difference between that crossover boundary when the talker is a woman compared to when the talker is a man. And we observe this effect when you have the whole vowel, like about 200 milliseconds worth. And if we take away the vowel, then there's obviously no context to drive any context effect. But if we carefully control how much of the vowel you get exposed to, the question is how much do you need before you demonstrate full separation between these labeling functions? As it turns out, you need only somewhere between 20 and 30 milliseconds, which is actually particularly common for a time window that drives a lot of different auditory processes. So the question we have next has to do with hearing. So these are our data for people with normal hearing. And so the question was, what about people with cochlear implants? We know they have a tough time hearing cues for pitch and frequency, but as it turns out, they actually do show phonetic accommodation of gender. So this was really surprising to us for the reasons that we've already gone over before. So we decided to look a little deeper into which cues they could be using. So when you look at the acoustic differences between women and men, there are a lot of them, but we're going to point to some of them that lie within the vowel here. A common thing that we think of is the fundamental frequency, or the pitch. So we have a lower rate of repetition for a man's voice compared to a woman's voice, but also in the formant frequencies. If you look at where those are for the woman's voice, if you scale them down in frequency, then you'd get something that sounds a little bit more like a man's voice. So our shorthand terms for these are F0, or fundamental frequency, and vocal tract length. There are some other cues that we used in this experiment, but these are the two that really played the largest role. So just a reminder, we're looking at the separation between these curves here. So we'd have a small effect over here on the right compared to the large effect on the left. And what I'm going to do is just translate these from the labeling data and just directly show you the differences between those curves, because then it's easier to show you a lot of effects at the same time on the screen. We see a large effect for both listeners with normal hearing and with cochlear implants, but as I said, we want to decompose this into a number of different acoustic cues. For people with normal hearing, vocal tract length really dominates this effect. It almost accounts for the entire complement of cues that you'd see in the natural voice, but it's a lot weaker for people with cochlear implants who use fundamental frequency relatively more. For other details about these cues, I'll refer you to the paper, but we just want to focus on these two for now. You might be thinking to yourself, I thought cochlear implant listeners had poor pitch perception, and you would be right. So how did they use pitch in this experiment? Well, to think about this, let's think about how pitch is encoded in the auditory system. There are basically two mechanisms, the place code and the rate code. For the place code, you can think about it the way you think of a spectrum, but of course in the auditory system, the frequencies aren't linear, they're logarithmic, so we can think about it this way. And what we see here is an idealized spectrum, but because we're dealing in a biological system, there of course is going to be a proper excitation pattern that we can see drawn here. So you can see that for the first 7 or 8 harmonics, each one gets its own place of activation, and that's our place code. But for the upper frequency harmonics, the place code breaks down because they're so close together that they can't be differentiated in the cochlea. So that's actually where the rate code takes over, because when you have two different components interacting together, they produce a temporal modulation that, as it turns out, is tied perfectly with the fundamental. So we get cues for pitch all across the spectrum, not just in the first harmonic. But the problem with cochlear implants is that the stimulation is delivered by electrodes whose positions don't change if the pitch changes. Furthermore, their fields of electrical activation overlap quite a bit, so there are just no harmonics in the signal at all if you use a cochlear implant. So the only access to pitch you have is in the time domain, these elements of periodicity in the speech signal. If we look at the pattern of electrical activation with these little orange bars referring to the electrode pulses, you can see that for each little bump in the speech signal, we get a corresponding bump in the electrical pattern. At least we do for a low frequency sound. When the sound is higher frequency, then that electrical pattern can't really keep up with it. So we have two things really going against us here. First, we're just not very good at using rate pitch. If we have harmonics, we're something like 30 times better at perceiving pitch than if we just rely on the timing. But also, even the timing cue here is not really good enough to fully differentiate ranges of pitches that we'd see in adult women and adult men. So it's a pretty weak cue, but still cochlear implant users can seem to use it somewhat. So what we tried to do here is ask the question, if listeners with normal hearing were relegated to using only that weak cue, would they be able to use it? So we used the same fricative sounds as before, but this time paired them with noises that had no harmonics, but which were filtered to sound like vowels, and we imposed an amplitude modulation with either a fast or a slow rate, like this. And so if you could use this cue to account for gender-related phonetic differences, we'd expect to see results that look like this, with separation between curves corresponding to the low or high rate pitch. But instead, there was no effective rate pitch for normal hearing listeners, even though people with cochlear implants appear to use this cue. So the final note that I want to end on is a pretty recent thing that we've done, and which I think the audience will find pretty interesting. Suppose we take the conventional way of looking at cue weighting, where we have two cues, for example, a formant cue here and a spectral tilt cue over there. You can create a psychometric function for each of these cues and find that the formant cue has a really steep function and maybe the other one's shallow, or maybe these get reversed. But maybe, as you're considering these slopes, maybe you use both cues, or maybe you don't use either cue very well. Perhaps there's something interesting that could come out of this kind of thought process. So what I'm going to do is just plot for you here the actual numbers for those slopes of those functions. So this dot would mean full reliance on the formant cue, not much attention to the spectral tilt cue. And this is the opposite. You have a high mark for spectral tilt and a low mark for formants. And we expect the data to look like this, where they're anti-correlated. The more you use one cue, the less you use the other cue. And we'd call this cue trading, and we can plot a regression line against this, and it looks beautiful, right? But as it turns out, this is not all the data we have. This is the full data set where the correlation really has gone completely away. So we thought about this a little bit more, and when you think about it, this person here at the origin doesn't use formant cues or spectral tilt to categorize the sounds. So here's a special case that we didn't expect. So we looked into how well people used both cues in tandem, and in this distribution, we can see the formant cue weight plus the tilt cue weight, and we get a nice distribution where the person at the origin would land right there at 0. And so what we did is we drew a line at the 25th percentile and just said everyone to the left of that is just not a very successful cue perceiver. So if we go back to the graph here and draw that line dividing those two groups, we can see what's coming, right? So we can see a different kind of correlation for people below the 25th percentile compared to people above it. And if you're not comfortable with the arbitrariness of 25%, we can change that to 20, to 15, to 10, and it still gives us the same story. And in the paper, we use 25, so I'll show that visualization here. What we're showing is a group that shows cue perception that's ultimately good enough that the cues can be traded, and another group whose perception is so poor that there's no trading. So if the cues are perceptible, they seem to be weighted, but if the cues are not easily perceptible, they appear to be integrated. So to recap everything I've shared with you today here, spectral and temporal cues can trade off in importance, and the use of those cues is obviously related to your psychoacoustic acuity. Spectral degradation leads to more lexical bias, The use of visual cues is consistent with articulatory sequences, not just segments, and the visual cues to gender can affect gender-related phonetic accommodation as a proxy cue for the auditory domain. Phonetic accommodation is driven primarily by vocal tract length cues for people with normal hearing, but for people with cochlear implants, they appear to use some pitch cues that would be relegated to the rate of modulation, which is totally ignored by people with normal hearing. Accommodation of gender in phonetic labeling can occur with as little as 20 to 30 milliseconds of exposure to the vowel. And the final point is that when cues are very difficult to perceive, they might be integrated rather than weighted. So I hope this can give you some interesting ideas about how to think about phonetic perception with an auditory and biological framework, which might open up some new ideas and perspectives for how you think about perception. Feel free to contact me if you have any questions about this work.